At first glance, quantum mechanics and special relativity seem like two great triumphs of modern physics, each elegant, powerful, and experimentally confirmed to astonishing precision. Quantum mechanics describes the behavior of particles at the smallest scales, electrons in atoms, photons of light, and the strange probabilistic nature of existence itself. Special relativity, on the other hand, revolutionized our understanding of space and time, showing that the speed of light is a universal constant and that time can dilate or contract depending on motion. But when you try to bring these two theories together, especially in extreme regimes like high-energy collisions or near the speed of light, paradoxes start to emerge. This uneasy marriage leads us into one of the deepest puzzles in theoretical physics, the relativistic quantum paradox. Let's begin with the basic question: what happens when a quantum particle moves close to the speed of light? Classical quantum mechanics, think Schrödinger's equation, doesn't account for relativistic effects. Schrödinger's wave equation assumes a fixed time and space background, treating time very differently from space, which violates the very core of Einstein's special relativity, where time and space are intertwined in a four-dimensional space-time fabric. To fix this, physicists tried to formulate relativistic wave equations, the first major attempt being the Klein-Gordon equation, followed by the Dirac equation, which elegantly predicted the existence of antimatter. But here's where it gets weird. When solving these equations, especially the Dirac equation for electrons, physicists found negative energy solutions. At first, these seemed like mathematical anomalies, but then came the realization these negative energy states might correspond to real physical phenomena, specifically the existence of antiparticles. In Dirac's theory, a missing negative energy electron behaves just like a positron, the electron's antimatter counterpart. This was later confirmed experimentally. In other words, trying to make quantum mechanics compatible with relativity didn't just tweak old ideas, it forced the discovery of entirely new particles. So far, so good, but the paradox deepens when we ask, how do we define a particle in a relativistic quantum world? In non-relativistic quantum mechanics, a particle is a stable entity. An electron in an atom stays an electron, but in relativistic regimes, particles can appear and disappear. High-energy photons can spontaneously transform into particle-antiparticle pairs. Colliding particles can annihilate into pure energy, and that energy can materialize into entirely new particles. And this creation and annihilation of particles is something standard quantum mechanics cannot handle. You need an entirely new framework. Quantum field theory, QFT. Quantum field theory resolves the paradox by treating particles not as permanent entities but as excitations of underlying fields. The electron is an excitation of the electron field, the photon of the electromagnetic field, and so on. In this view, empty space is not truly empty. It is a boiling sea of virtual particles, constantly forming and annihilating. Fields fill all of space-time, and particles are simply quantized vibrations within them. This is the only way to consistently reconcile quantum principles with the demands of relativity. But QFT brings its own conceptual challenges. For one, the vacuum is no longer simple, it has structure. It can polarize, fluctuate, and even change under different boundary conditions, as in the Casimir effect. And defining what counts as a particle becomes murky in curved space-time or accelerating frames. Consider the Unruh effect. An accelerating observer in a vacuum will perceive a warm bath of particles, while an inertial observer sees none. So, is there really a particle there or not? The answer depends on who is looking. Another strange twist arises in entanglement and causality. Quantum entanglement allows particles to influence each other instantaneously across vast distances, but relativity forbids faster-than-light signaling. The solution is subtle. Although entanglement correlations are instant, they cannot be used to send information faster than light. This maintains causal consistency, but the tension remains a core feature of the relativistic quantum world. And perhaps the most striking paradox appears when you try to include gravity. General relativity describes gravity as the curvature of space-time, while quantum theory demands flat space-time for its fields to behave properly. Try to merge the two, and you run into infinities and inconsistencies, black hole evaporation via Hawking radiation, leads to the information loss paradox, where quantum theory says information should be preserved, but relativity suggests it might be lost in a singularity. This has led to decades of research into quantum gravity, string theory, and the holographic principle, all attempts to resolve the relativistic quantum paradox at its most fundamental level. So what challenges arise when merging quantum mechanics and special relativity? The very definition of a particle changes. Time and energy become entangled in strange ways. Particles can pop in and out of existence, and observers no longer agree on what is real. It forces us to abandon the classical picture of isolated objects and embrace a universe of dynamic, probabilistic, and deeply interconnected fields. Could solving these paradoxes lead to a final theory of everything? Perhaps, but for now, the relativistic quantum paradox stands as both a caution and an inspiration. The closer we look at nature, the more reality resists simplification, and the more we are pushed to expand our understanding of what real even means. Traditional Schrödinger quantum mechanics assumes a fixed number of particles and lacks Lorentz invariance, making it unable to describe processes in which energy transforms into matter or vice versa. When naively combining the Schrödinger equation with relativity, one obtains negative energy solutions that defy physical interpretation, signaling a deeper inconsistency that necessitates a framework in which particle number is not conserved and creation and annihilation events occur naturally, leading directly to quantum field theory, where fields, not wave functions, are the fundamental entities. The Klein-Gordon equation yields both positive and negative energy solutions for a free relativistic particle, forcing reinterpretation as particle-antiparticle pairs. It's like trying to describe water flow with a model that assumes the number of water molecules is fixed, even though steam can evaporate and condense, leading to nonsensical predictions. Relativistic wave equations predict solutions with energies below zero, implying that particles could cascade into ever lower energy states and release infinite energy. This vacuum instability paradox disappears only when the vacuum itself is redefined as a sea of filled negative energy states whose excitations manifest as antiparticles, so particle creation corresponds to promoting a negative energy whole to a positive energy state, elegantly explaining antiparticles and making the concept of a dynamic vacuum with creation/annihilation operators indispensable. Dirac's hole theory explained the positron as a hole in the negative energy electron sea. It's like filling every seat in a theater. A sudden empty seat, hole, behaves like a positively charged entity even though all actual seats, holes, remain present. Special relativity requires that no influence travels faster than light, yet naive quantum interactions can imply instantaneous action at a distance, so ensuring causality demands that field operators at space-like, separated points either commute or anti-commute, forbidding superluminal signaling. This locality constraint is incompatible with fixed particle quantum mechanics but naturally satisfied in quantum field theory through local field interactions, ensuring particle creation and annihilation events respect causal structure only within a field framework. Two detectors measuring a field at space-like separation yield uncorrelated outcomes, preserving causality. It's like having fire alarms wired so that a trigger in one room cannot instantaneously set off an alarm in a distant room without a causal connection. In high-energy collisions or strong fields, energy can convert into new particle-antiparticle pairs, a phenomenon impossible in single-particle quantum mechanics. So, relativistic quantum field theory treats particles as excitations of underlying fields, with creation and annihilation operators encoding these transformations and allowing a consistent description of scattering processes and decays that satisfy both energy momentum conservation and relativistic covariance. Without this mechanism, predictions of phenomena like pair production would be unattainable. Electron-positron pair production occurs when a gamma photon of sufficient energy interacts with a heavy nucleus. It's like converting electricity into light bulbs, particles, on demand, and then reabsorbing them back into energy Relativistic fields possess intrinsic quantum fluctuations even in their ground state, giving rise to virtual particle creation and annihilation that influence observable quantities and demonstrate that the vacuum is not empty, as manifested in phenomena such as the Lamb shift and Casimir effect. Accounting for these vacuum fluctuations requires renormalization to tame infinities arising from summing over all possible virtual processes. Underscoring that particle number is inherently indefinite in relativistic quantum theories, the Casimir force between two conducting plates arises from altered vacuum energy due to boundary conditions. It's like a restless crowd in a stadium, creating pressure even when no actual game is being played. Tiny fluctuations exert measurable force. Calculations of particle creation/annihilation loops in relativistic quantum field theory produce ultraviolet divergences, mathematical infinities from summing over all high-energy modes. So renormalization systematically absorbs these infinities into redefined physical constants, yielding finite predictive results. This procedure is unique to field-based theories where particle number can vary and has no analog in fixed particle quantum mechanics. With successfully renormalizable theories like quantum electrodynamics demonstrating the consistency of merging relativity and quantum principles, the electron's self-energy correction diverges but can be renormalized to match its observed mass. It's like trimming excess material from a sculpture until only the intended form remains visible. Relativistic invariance enforces a deep link between particle spin and statistics. Integral spin particles obey Bose-Einstein statistics, while half-Miniger spin particles obey Fermi-Dirac statistics, a connection that emerges only in field theory where creation and annihilation operators satisfy commutation or anti-commutation relations, with the spin statistics theorem guaranteeing stability of matter and the existence of antiparticles as required by relativistic symmetry. Without it, paradoxical predictions like negative probabilities or unstable vacua arise. Photons, spin-1 bosons, can occupy the same state, whereas electrons, spin-1/2 fermions, cannot, preventing collapse of atoms. It's like a parking garage rule. Buses can stack side by side, but cars each need a dedicated spot. Relativity and quantum mechanics predict that particle content of a field depends on the observer's motion. An accelerating observer detects a thermal bath of particles, Unruh radiation, where an inertial observer sees vacuum, illustrating that particle creation and annihilation are not absolute events but frame-dependent, challenging our notion of what constitutes a particle, and demonstrating that field operators remain the invariant reality while particle number becomes emergent. An astronaut accelerating through vacuum would perceive a temperature proportional to their acceleration. It's like stepping onto a moving walkway where the scenery particular content shifts depending on whether you stand still or walk. Quantum field theory, QFT, seamlessly integrates quantum mechanics with special relativity by treating particles as field excitations and accommodating creation/annihilation processes while enforcing Lorentz invariance, causality and probability conservation, and providing calculational tools, Feynman diagrams, and renormalization for predicting scattering amplitudes. It resolves paradoxes of negative energies, frame-dependent particle definitions, and vacuum instability, establishing a consistent framework for high-energy physics and standing as the only known theory reconciling relativistic and quantum principles in a predictive, experimentally validated manner.